Welcome to episode 06 of CipherVibe's end-to-end cloud security architecture course. Network isolation organizes cloud reachability around purposeful boundaries. It limits which systems can communicate, reduces lateral movement, and makes public, application, management, and data paths easier to reason about. We will connect its purpose, design boundaries, implementation path, failure modes, and evidence of effectiveness. Every cloud security layer relies on the ones around it. It uses identity and authorization to control administration, workload policies to control service-to-service access, and logging to reveal unexpected paths. Segmentation becomes more valuable as cloud services, accounts, and data classes multiply. Treat the architecture as a chain. A trusted identity requests an action, a policy makes a decision, a workload or data service enforces it, and telemetry records enough context to investigate later. The first building block is create meaningful network boundaries. Use VPCs, VNets, projects, accounts, or subscriptions to separate meaningful ownership and risk domains. Keep production distinct from development, define approved interconnection paths, and avoid a flat network where any workload can discover and reach unrelated systems. The second building block is use tiered subnets intentionally. Design subnets for the function they serve. Public subnets should host only controlled entry points. Private subnets should host application components with explicit egress, and database or sensitive data tiers should have the narrowest paths, no casual internet route, and restricted administration. The third building block is enforce least reachability. Write rules in terms of approved sources, destinations, services, ports, and direction. Use identity-aware groups or tags where possible, restrict egress as well as ingress, and remove broad network ranges that turn a temporary troubleshooting change into permanent lateral movement. The fourth building block is add micro-segmentation at runtime. For containerized and dynamic systems, add workload-aware controls such as Kubernetes network policies, service mesh authorization, or host firewalls. These controls express which services may talk to each other even when addresses change, and they can be validated against normal application dependencies. Use this reference pattern. Begin with an explicit policy that describes the permitted outcome. Enforce that policy at the closest reliable control point. Route decision and activity evidence to protected storage. Then give an accountable team a tested path to review exceptions, correct drift, and respond to violations. A layered design separates public entry, applications, data, administration, and shared services, then uses explicit policy at each hop rather than trusting address range or cloud location by itself. Implement this layer in a sequence that preserves evidence and limits blast radius. First, map current ingress, egress, routing, peering, and private endpoints. Second, define target zones by environment, data, and ownership. Third, move public exposure to controlled entry services. Fourth, restrict security group and NSG rules to required flows. Fifth, add micro-segmentation for critical east-west paths. Prefer pilots with a named owner and rollback plan over an unmeasured organization-wide switch. The best rollout is one where a normal workflow succeeds, an unsafe path fails closed, and the team can explain the decision from logs rather than intuition. Security architecture fails most often through assumptions, not dramatic movie-style attacks. First, creating subnets without changing overly broad security rules. Second, allowing unrestricted outbound internet access from sensitive workloads. Third, peering environments broadly without shared governance. Fourth, relying on IP addresses alone in highly dynamic container platforms. A configuration screen is not assurance. Collect evidence that the intended control applies to the correct scope and that violations become visible. First, maintain a current allowed flow diagram and rule inventory. Second, test approved application paths and denied lateral paths. Third, monitor flow logs for unexpected destinations and admin ports. Fourth, measure public exposure, broad rules, and isolated data coverage. Test both normal activity and a safe negative case in an authorized environment. Record the expected decision, the evidence location, the owner who reviews exceptions, and the rollback method. Repeat after platform changes, new integrations, or major shifts in business use. For a practical exercise, create a network design for a public application, private API tier, and isolated database with one shared logging service. Use synthetic information or an environment you own or are explicitly authorized to administer. Deliver a one-page diagram, a concise control statement, a list of expected audit events, and one test for an allowed path plus one test for a denied path. This artifact is more valuable than a screenshot because it explains the reasoning behind the configuration. Before scaling this layer, ask 5 review questions. Which assets, identities, or environments are in scope? Who owns the desired state and exception decisions? Which enforcement point can reliably apply the rule? Which records prove the decision and retain enough context for an investigation? And how can the organization revoke access, contain impact, or roll back safely when a control fails? Good architecture makes these answers explicit and testable. The key lesson is that network isolation becomes dependable only when design, policy, enforcement, evidence, and ownership move together. Document the decisions you make, remove permissions and exposure that do not support a real requirement, and rehearse the paths that matter before an incident forces the lesson. Continue through the next episode to connect this control layer to the rest of the CipherVibe cloud security architecture.